Example number 9. This is involving 3 resistors that are connected at both ends of the resistor. So the right side of resistor 1 and 2 and 3 are all tied together, and the left side of resistor 1 and 2 and 3 are all tied together. So this right here, this point is a junction here, A, and another junction at B. And that current that is flowing from the battery, I, will be coming in along here, coming to A, and then it will split into 3 different paths. We have I1, we have I2 going through resistor 2, and then lastly we have last current here, I3. And those currents will then recombine here at B and then come back and provide that same current I that is being drawn through the battery. So we have 3 resistors of 2 ohms, 4 ohms, and another 4 ohms. Now on the note packet I accidentally, this was written as W, but they really should be ohms. And the battery is a 5-volt battery with an we're assuming this is an ideal battery with no internal resistance. So first thing we're going to do is we're going to try to find the individual currents through 1, 2, and 3. So one thing one needs to realize is that the potential difference across each resistor, R1, R2, and R3, are the same because each resistor is connected in parallel. They all have the same potential drop. Whether you take this path over this branch, R1, or the middle one, or the bottom one, all 3 branches have the same potential drop because they start at the same point and then they end at the same point. So it doesn't really matter what path that you take because you still have the same amount of energy per coulomb that is being lost. And those 2 points A and B is also the same really as the potential drop or increase over the battery. So let's actually answer C because that's really what we were just discussing here. Let's do C. This is a little bit out of order. The potential drop of 1 and the potential drop of 2 and the potential drop of 3 are all equal to that EMF that is given, which is 5 volts. And that's it. You're done for part C. Okay, so now let's move on to finding those individual currents because now we know they all have a 5-volt drop and we know their individual resistances, so then we can proceed on using Ohm's law. Remember, V equals IR, so therefore I would be equal to V over R. So you would use the voltage of 1, which is 5 volts, all over the resistance of 1. So we have 5 volts divided by a resistance of 2 ohms. And that will give you 2.5 amps for current 1. And similarly, we can apply that to R2 and R3. So I'll go ahead and do that now. Okay, and so then you can see now we have 1.25 amps going through the middle one and then 1.25 going through the bottom branch. Those are both the same currents because they both have the same resistance. And notice that the resistor that has this smaller resistance, which is 2 ohms for number 1 resistor, the top branch will have the higher current because the current is going to take the path of least resistance. So the bulk of the current that comes into junction A will go up through I1 and the rest will split through 2 and 3. And this splits through 2 and 3 equally because they have the same resistance. So we've completed that task now, finding the current through each resistor. And now we can go ahead and calculate the total current. The total current you can do a couple ways, but since you know all the individual currents, you could calculate that total current by using the sum of the individual currents that leave that junction A or enter junction B is equal to the total current that comes from the battery or goes into the battery. So that would be adding essentially each of these currents, 2.5 amps plus 1.25 amps plus another 1.25 amps, and that gets you a total current of 5 amps. Okay, so there's 5 amps leaving the battery, then 2.5 amps, half of that goes through resistor 1, and then this is then split up. The other quarter and a quarter goes through resistor 2 and 3. So now let's move on to figuring out which bulb is the brightest bulb. So we're going to look for the power that is dissipated across each resistor. Now once again, you can use 3 different ways to calculate that power. You can use I times V, you can use I squared times R, and you could use V squared over R. Any one of those work because you now know each of their individual currents, I1, I2, and I3, you know all their voltages, and you happen to know all the resistances as well. Now, if I were asked to find out which bulb is the brightest, I would be looking here and saying the resistor with the least resistance is actually going to have the brightest bulb. when I compare light bulbs that are all in parallel, I know they all have the same voltage. And since the voltage is the same for all of them, it's easy to see that the power is inversely related to the resistance if the voltages are all the same. So I'm going to head and calculate the power by using V squared over R for each one. So power 1 and then over equals voltage squared over resistance 1. So that voltage for all of them is that EMF of 5 volts squared divided by resistance 1, which is 2 ohms. And so go ahead and calculate that. I get 12.5 watts, and then I can do a similar thing for light bulb 2 and 3. Okay, and so we see that power 2 is 6.25 watts, also power 3 because they're both the same resistance. And the brighter bulb is the first bulb because it has the lowest resistance. So now the last part is to find the total power delivered by the network of resistors. Again, you can do it several ways. You could use the total power is equal to the total current, which would be 5 amps multiplied the total voltage, which is 5 volts. You could again or use I squared times R. Remember, R would be R equivalent, or V squared over R. I'll just stick with the same formula using V squared over R since that's what I used last time. So now my voltage was 5 volts squared divided by my equivalent resistance, which was, didn't calculate that. I guess I could have calculated that. That equivalent resistance would be using 1 over R1 plus 1 over R2 plus 1 all over R3. That's 1 over resistance of 2 ohms, 1 over 4 ohms plus 1 over 4 ohms. So if I do a common denominator, that would be 4. And so I would get 4 ohms over 4 ohms. That gives me an equivalent resistance of 1 ohms. I should have made a little correction here. And there we go. So now that's 1 ohm in here. If we put 1 ohm in there, we'll have a total power of 25 watts. Now alternatively, it would have been easier if I had done I times V or I squared times R. Or I could even just have done power equals power 1 plus power 2 plus power 3. And simply add up 12.5 watts plus 6.25 watts plus 6.25 watts. And that will also give you 25 watts, which is the total power driven by that circuit. All right, and that's it for this example on parallel circuits.